today we want to tackle one final subject still within this view of renormalization by counterterms before we move on to more involved, maybe deeper ways of renormalizing theories, right? And the point is that so far we have considered the renormalization of mass for particles, right? But we always had in mind stable particles, right? I never worried too much if the physical mass was really well defined or not, right? But we know that in our daily lives, most of the matter we see around us is made from very few stable particles, right? The electron, the proton, the neutron, right? But every other particle we see in high energy physics decays, right? Most of them decay. And so today we want to just see how can we change this mass renormalization when the particle is unstable, and how far can we take that kind of renormalization in this case. This discussion starts with something called the optical theorem, and which is a consequence of one of the cornerstones of quantum theories, right? Either quantum mechanics or quantum field theory, which is unitarity, or in other words, the conservation of probability, right? What we want from any quantum theory is that the probability of any thing happening to be one, and that continues to be one as I evolve my system through time, right? That can be translated to the normalization of the states, right? So I can demand that a state, say in the Schrödinger picture, so I put all the time evolution in the states, right? The normalization should evolve so that it doesn't change as my system evolves through time, so that probability is conserved, right? Of course, that implies something for the Hamiltonian of the system, because we know that in this picture, right, the states evolve according to the exponential of the Hamiltonian times time, and that means, of course, immediately that the Hamiltonian should be Hermitian, right? This is the constraint on the Hamiltonian. In the case of quantum field theory, we know that we're mostly interested in the S matrix, the scattering matrix, which is defined in this way. So if I use this hermiticity of the Hamiltonian here, right, I immediately conclude that the scattering matrix should be unitary, right? So this is what I get for the scattering matrix. And we'll see that this has consequences, and one of them is the optical theorem. So let's try to see what that is, right? So the first thing is to translate this constraint in S to the transfer matrix, right? That we defined before as 1 plus IT, right? We defined this is the transfer matrix. Now I can plug that definition in here, right? Which will give me this expression. And then I can just do this algebra here and rewrite these in terms of this condition for T. And now I can use this. As we know, the T is very closely related to the matrix element that we used inside cross sections, right? So I want to translate that to a constraint to those matrix elements, or even the cross sections themselves. In order to do that, I'll just take any initial state, right? So take this equation here, and I'll contract to the right with an initial state can be anything. And to the left with some final state, also arbitrary, right? And rewrite this equation. Now what I get, I can move these factors of I outside. This will be just I, F, T dagger, IFT dagger I, initial state, minus I, F, T, initial state. This is the left-hand side of this equation. Now the right-hand side will be simply F, T dagger, T dagger, T, I. And now I want to message, right? Try to put these in a more convenient form, right? First thing to notice is that this piece right here is just I, T, F, dagger, but since this is a complex number, I can just use the complex conjugate, right? And on this right side, I want to insert right here a set of an identity, right? Written in terms of a complete set of 1, 2, 3, 4 particle states, right? I can write that as a sum over x, right? Some integral in momenta. I'll just specify exactly what this integration measure is here, right? And this operator right here, right? Which is summed over 1, 2, 3, 4, n particle states, right? This is a complete set, right? And this d pi x here will be defined as just the product with j belonging to this x of d3pj over 2 pi cubed 1 over 2ej. So I'm using the relativistic normalization for those states, right? And I'm simply integrating over all the momenta of all the particles in here, right? So I'm just taking an n particle state and integrating over the momentum of each of those particles, right? And I'm putting this in here. So now let me rewrite this. I also want to use, right? Let me rewrite the right-hand side first, just to avoid confusion. So now I have this sum, this integral right here, right? And I have this piece contracted with x, and then the other part right here. Oops, I missed a part of my t. There you go, right? Didn't miss anything. Now I want to use the definition we usually do for this guy, right? We know that we have defined many times before this guy as the conservation of momentum. There's a factor of 2 pi over here, the delta 4 of the sum over initial and final momenta times, right, the actual matrix element that we use for cross-section. So I want to use that definition here, here, and in these two elements on the right. So let's start with the left-hand side of this equation. So let me just color stuff, will make it easier to follow what goes where. Right? On this left-hand side, it's easier, right? Because it's the same initial and final momentum. Let me just do the replacement I mentioned up here because I didn't do it. I, T, F, complex conjugate, right? It's the same momenta in the initial and final states, right? It doesn't matter, it's reversed. So this conservation of momentum part is the same, which factors in front. So let me repeat that. There's an I, then 2 pi to the fourth, delta 4 of pi initial minus p final, right? And then this complex conjugate will hit this m right here, right? And so these will become just m star. And now it matters, right? This is going from F to I. And the other part here is the usual M I to F. Right? So this is the left-hand side of this equation. And on the right-hand side, I have to do it for these two pieces, right? That won't fit there. So let me put it down here. Let me bring this guy here, just so we see stuff, right? So now for the green part here is 2 pi to the fourth, delta 4. Now the sum is over the final momenta and the x, the sum over all the momenta in the state x. And then m, again, I have a dagger here, so it will be an m star x going to F. Now for the purple piece here, it's just 2 pi to the fourth, delta 4. Now the sum is over the initial momenta minus the momenta of x. And again, I have a m of I to x. I hope I didn't forget anything. No, that's fine. So now I can simplify stuff a little bit, right? These Dirac deltas, right? One impose something on the other one, right? I'm integrating over the momenta x, right? But this total sum is fixed by this delta. So I can just replace, say, on this one, I can replace px by pi because this is imposed by the other delta. If I do that, then I can have a cancellation. Well, the factor of 2 pi to the fourth, of course, but then this delta is also, I'm also able to eliminate it with this one because this is guaranteed by the other delta, right? In that case, what I obtain, right, I eliminated everything. There's a I left over here, which I'll send to the other side. And that means I have to exchange this sign, right? So I'll write these in this way. Right? I just change the sign to get a minus I here and send the I to the other side of the equation. I'll put it here, right? And then I just repeat everything that didn't go away. This comes here. And I have these two matrix elements here. This one and this one, right? And this is important result. This is called, let me put a box around it, the Generalized Optical Theorem. And keep in mind, I just fixed this direction here, which was wrong a few seconds ago. Okay? One thing to notice here, there's a few important points in this theorem. Right? The first thing is that on this side, I have something that is proportional, right? If you look here, this is of the order of m square, right? I have m star here for the matrix element, right? This is just a sum of integrals of m square. So suppose I calculate these matrix elements in perturbation theory at some order lambda. Suppose there's some coupling and I calculate these guys at order lambda. On the left hand side of this equation, I don't have m square. right? I just have m. This is just m minus m star. And that means that if I want to match in perturbation theory, right, this can only be equal if these guys are calculated at order lambda square. So the first thing to notice is that this is relating diagrams, right? If I translate these to Feynman diagrams, is related diagrams that on the right side will be calculated at one order and on the left-hand side at a higher order in perturbation theory. And that means since I'm keeping these external legs fixed, right, that means that essentially I'll go to loops on the left-hand side, right? If I have three level diagrams on the right-hand side. And that also is important because if this is just a requirement, right, the only thing I'm requiring here is unitarity. And that means that loops will also play an important role in keeping unitarity in these quantum field theories. You cannot keep it without the loops, right? So that's the first thing to notice. Now, let's see what happens, right, when we specialize this for a particular case, which is when the initial and final states are the same. So let's say I get some initial state, some final state. I still keeping these guys pretty general, but now I'll just say they are the same and call that state A, right? In that case, if I go back here, I and F will be the same, right? And then I'm subtracting this guy from itself complex conjugate, right? So on the left-hand side, I get 2 times the imaginary part of this m of a to a, right? Because the same thing will appear here and here, right? So I'll subtract, eliminate the real part and get 2 times the imaginary part. On the right-hand side, not a lot happens. I can repeat most of these things. I think the box will come with it. Let me delete the box, right? Now, this is just PA, right? That's one of the changes here. And of course, now these two matrix elements are just from A to X. So essentially I get M of A to X modulus square, right? Which is another, let's say, specialized version of the generalized optical theorem. Now, let's see a few particular cases where we can understand a little bit what's the physical content that is contained here, right? One specialization which is pretty useful is to take this A state to be a one particle state. So now I'm thinking of a one-to-one transition here, right? Essentially a propagator. Then I can rewrite this guy in terms of a decay width, right? Now you have to remember some calculations we did in quantum field theory 1, but we have shown that the decay rate of A to any state, right, is given by just 1 over 2 ma integral over the final phase space for this X state, which again is the same thing we just defined, right, times 2 pi the fourth delta 4 PA, which is the momentum of this initial state, which is just one particle, to Px, right, the sum of the final states in which this particle decays, right, times this matrix element from A to X square. You can see how this is very similar to what we have in the right-hand side here, right? Basically the same thing other than some factor of mass and I right there, right? And that means I can rewrite this imaginary part of the one-to-one transition as the mass times the sum over all possible final states, because I have this sum, right here, right, of the decay of A to X, right? I just used, right, there's a factor of 2 here, the i's eliminate right here, right? So essentially I just multiply the A on the other side, right? And remember that I have this sum over X. The rest I have here is exactly this expression. So I related the imaginary part of a one-to-one transition to a one to n. So let's put imaginary here so we don't forget, right? To the total decay width from 1 to x, right? And the sum over x, if you remember, that's also a discussion we had in quantum field theory 1, right? You might remember that we call this decay into a particular set of final states, a partial decay width. So there are particles that have many possible decays, right? Take the W boson, it can decay to electron-positron, or it could decay into quarks, right? It has a different partial width, which is the decay rate in each of these so-called channels, which are these possible final states, right? In this case, I'm summing over everything that is possible. As long as this decay rate is not zero, right, which will be zero if I violate charge conservation, if there's no phase space, the final states are too heavy, so I cannot conserve energy and momentum here, right? All these decay rates will be zero, so I'm summing over the ones that are possible, right? And this total sum is what I call the total decay width, right, for a particular particle, right? This is the total decay rate, and this is the guy that is related to the lifetime of that particle, right? The bigger this is, the smaller the lifetime of the particle. They are the inverse of each other, right? So I just related, using the optical theorem, the imaginary part of one-to-one to the total decay width of the particle, which is interesting, right? Kind of unexpected from the start. It's a non-trivial consequence of unitarity. Okay, so this is the one-to-one case. And now let's see another example, which is the two-to-two case. So let's now think of a two-to-two scattering. Right? So now we're assuming this generic state A here, right, is actually a two-particle state. So we're assuming A is equal to K1, K2, right? So now this equation right here becomes twice the imaginary part, or eliminate this factor of I on both sides here. So it's just the imaginary part of this matrix element from K1, K2 to K1, K2, right? This is the important part. Here, since we're assuming the initial and the final state are the same, right? This is a forward scattering, right? You have two particles coming at each other and they leave in the same direction, right? This does not mean that they didn't interact, but you produced them back in the forward direction, right? On the right-hand side, I'm just copy that thing. Right now the sum is over all the possible intermediate x states. This is the phase space for x, 2 pi to the fourth, delta 4 now is k1 plus k2, which are these two momenta here, minus the sum of p of these x states, right, times the matrix element from k1, k2 to x, right, modulus square, right? So now I can roll back. We don't need that equation anymore. And we can see what can we extract from these two scattering. The first thing to notice is that these we can put these equation into diagrams, right? And notice it has a very suggestive form. So I can write this as 2 times the imaginary part of this diagram, right? This is K1, K2 going to K1 to K2. Anything can happen in the middle, right? And this is being expressed in terms of the sum over x, the integral over the phase space, right? Of actually this product of two m's here, right? One which is K1, K2 to x, right? Without the complex conjugate is actually this diagram, right? And the complex conjugate of this, which is in here, is actually the other direction, right? Is this diagram. So you see, this is very suggestive because it says that the imaginary part of this loop, right? As I said before, even if I consider these guys on the right at the lowest order, so I have some 3-level amplitude that connects these two lines to these n final lines, right? On the right side, I'll have to go one order up in perturbation theory, and that means I'll have loops here, right? And what's happening is I'm looking at some very complicated diagrams that can happen in the middle here. And the way I write the ones on the right is like I cutting this guy in the middle here somewhere. It's like I'm doing a cut here and exchanging my propagators for these scattering of on-shell particles here, right? All these X states are on shell on these scattering amplitudes, right? And this sum over X here means that I'm doing these cuts in all possible ways here. And what possible means? Possible means that the scatterings on the right-hand side are not zero, right? So for instance, if I do a cut and I don't have enough momenta here in K1 and K2 to produce all these X states, these will be zero, right? Because I have to produce them on shell, right? So this will be zero, and that means that that particular intermediate state X won't contribute to the imaginary part of this loop that I'm cutting here, right? Also charge conservation, everything that could make one of these guys zero will make it so they don't contribute to the imaginary part on this left-hand side, right? And again, I related an imaginary part of a 2 to 2 scattering to now some 2 to n scattering, right? N is the number of states in X, and I'm summing over various different values of n with the constraint that I should be able to produce this on shell, otherwise they don't generate an imaginary part on this left hand side, right? This is becoming very familiar, right? We have seen this happening for a few loops we calculated a few videos ago, right? That we only had an imaginary part once I could actually put these intermediate states on shell. And this is the general version of it, right? And it's nice to see that it comes from a very basic principle, which is unitarity. Now, again, I can rewrite this thing, the same thing I did for the one-to-one here, right? I could find on the right-hand side here the decay of A to X, right? I can do the same thing here because this expression looks a lot like a scattering of 2 to n, right? Like I mentioned here. Again, I have to appeal, let me keep this equation there so I can see, but I have to appeal to something that we did in quantum field theory 1, which is the general expression for the cross-section of a 2 to n scattering, right? And we have shown after integrating over phase space and doing all the simplifications you can do in that case that this is given by, in the center of mass, we can calculate this part in the center of mass reference frame, right? This will be 4 times the energy of the center of mass. This is the modulus of K1 also in the center of mass reference frame times the phase space for the x states times 2 pi to the fourth delta 4 of the sum over the initial state, so k1 plus k2 minus the sum over the moment of the final states times, of course, the same thing again. I'll just copy it. Right? And you see that this is basically this guy, right, up here, times some numbers, right? So I can again take this part that is common here and here, send this multiplying to the other side and substitute there. So I can write the imaginary part in terms of the cross section. So I can say that the imaginary part of this, also sending this factor 2 over here, right, is equal to twice, because of that factor 2, right, the energy of the center of mass, this value of momentum. The reason I'm putting K1 is because the modulus of K1 and K2 are the same in the center of mass. So it doesn't matter, right? I just choose K1. And now I'm summing over X, as usual, right? The cross section for K1, K2 going to X, right? Let me put a box around this one. Because this is the actual optical theorem, right? The one we saw before was actually a generalized version of this, right? Historically, the first place people have proven this theorem, right, was actually for light waves. That's why we call it optical theorem, right? People were looking to the forward scattering in light waves, right? And for classical waves, this is a consequence of the conservation of energy. Right? And for quantum systems, it is a consequence of the conservation of probability, which is quite nice, right? So that's why the optical theorem is for forward scattering, right? Now, the fact that only these on-shell intermediate states are contributing to the imaginary part of the loops on the left here even give us a method for obtaining imaginary part of loops. Suppose you're only interested in the imaginary part, there's a shortcut you can take. Instead of actually going through the whole calculation of the loop and having to deal with those complicated integrals, and then in the end finding out the imaginary part, you can actually use this to get directly the imaginary part, right? This is what is called the Cutkosky cutting rules, right? And it consists in looking for propagators inside those loops and exchanging the propagators, right? So you just replace propagators by Dirac deltas with the proper normalization, right? But you're forcing those particles on the mass shell, right? And you know that this is the only, and then it's much easier to do the integrals, right? If you do this substitution, right? And this guarantees that you're actually on the support where these particles go on shell, right? But what you're doing is looking only for the imaginary part, which comes from these on shell intermediate states, right? I won't prove this here, but you can find it. I'll put some references in the description of the video. You can find that in Schwartz and Peskin and Schroeder's book, right? But it's quite nice, right? You can just diagrammatically cut diagrams in all ways possible and get the imaginary part directly, right? And it's just one of these funny facts of life that make you feel like someone is making fun of you, that these rules for cutting diagrams, which actually we know the imaginary part of these diagrams is also coming from the branch cuts, right? You are actually calculating discontinuity across these. The imaginary part of these diagrams is the discontinuity through as you go through the branch cuts, right? And this was proven. This substitution rule was proven by someone named Cutkosky, right? It's a very funny thing. Now let's see one example of an application of the optical theorem, just to get a feeling for the thing and test if it really works in a particular example, right? Let's obtain the decay rate for a particle from the optical theorem. In order to do that, let's make a toy model here, just a theory with two different scalars. Let me write first this one. So there are two real scalars. One of them I'll call phi. So it has these Lagrangian. I'll give a mass to this phi, which I'll call this uppercase m phi square, right? This is the physical mass already. I won't write all the counter terms, nor because we won't really be looking into the divergent part or doing the renormalization. Assuming we already did it, and this is actually the physical mass for this guy. Now, I'll introduce a second scalar. It also needs a kinetic term. I'll call the second scalar pi. It also has a mass, which I'll use lowercase m. Okay. And of course, these two guys need to have some interaction, otherwise nothing happens. And I'll use an interaction that looks a lot like a 5-3 interaction. So just put a lambda over 2 phi pi square, right? So the Feynman rule for this involves one phi line and two pi lines with strength coupling lambda, right? Just to differentiate those two, I'll use a dashed green line for phi, right? So it has this uppercase M mass, and let me get it here, and a purple, oof, something else came with it, right? And a purple continuous line for pi, right? And the first thing I want to calculate is a one-to-one. Remember, I related the decay rate of particles to the imaginary part of one-to-one scatterings, right? So I'll calculate a one-to-one process for the phi particles. So I want to calculate these at one loop order, right? Because I need loops to be able to, remember on the left-hand side, I needed loops to relate to three level diagrams on the right side. I want to calculate the decay rate at 3 level. So I want to calculate the one-to-one scattering at loop level. So what I'm talking about here is a phi to phi one loop diagram is a function of some p momenta, right? So the diagram I have in mind is this one, right? So it's I start with a phi, right? I have this vertex coming from this interaction that produce two pi's, right? Which then annihilate to form this phi again, right? This is the first contribution to the self-energy of this scalar field phi, right? The Feynman rules for these are quite simple, right? I have this interaction twice. Also, there's a symmetry factor here, so there's a factor 1/2. This is the interaction twice, right? I have an integral over these momenta, d4k over 2 pi to the fourth, and then these two scalar propagators here, which are I k minus p square minus lowercase m, right? The guy in the middle is actually this guy, plus I epsilon. And the other propagator, right, is just I k square minus m square plus I epsilon, right? I won't actually integrate these, right? I can transfer the responsibility to you guys by saying that the interested student will check this out, right? But it's the usual Pauli-Wheeler's shenanigans, right? I can just use Pauli-Wheeler's here, all the tricks we have already seen many times, and get to this expression right here. So this is the Feynman parameter, the x log of lambda square, right? This is the Pauli-Wheeler's mass, right? It's the regulator for our UV divergence that is there, right? And in the denominator here, I have the usual delta, right? Which I'll write explicitly now x1 minus x minus I epsilon. Right? And this is the result for this integral, as far as we still have to do the Feynman parameter integral, and but that's exactly what we want to avoid, right? By only looking at the imaginary part. Right? So now we have essentially two cases, right? The first thing to remember is that when we're looking at a one-to-one scattering like that, this P here is on shell, right? I can think of this as really a one-to-one scattering. So these green lines are actually external lines. So I can actually replace P square by capital M square everywhere. So this guy is just minus lambda square. I'm just actually there's an I here, but there was an I there. This minus is because I'm flipping the order. Let me write this like that. Lambda square over 32 pi square. And this minus is because it's more useful for me now to write the log in this way. So I'll put this guy up. This guy down here, right? And I'm saying this is on shell, so capital P square is equal to capital M square. Right? So now we have essentially two cases here, right? In the case, I have to compare these two parts to see if I'm hitting any of the known analytices of this logarithm here, right? So again, as we did this again and again, it's always kind of the same form here. So if you remember well, this x, 1 minus x, right, is bounded by 1/4, right, as I integrate from 0 to 1 in x. And that means now that I have two different cases, right? The first one is when m squared, m actually, is smaller than 2m, right? In that case, m squared is smaller than 4 little m squared, right? And that means that this combination right here, right, is always positive. Let me write everything again. X, 1 minus x is always bigger than 0, right? That means I can take epsilon to 0 now with no issues, right? And then this log is there's no imaginary part to this log. This is actually the imaginary part of m loop is 0, right? That's fine. That's very similar to the analysis we did for the self-energy of the electron. Right? Now, on the other side, I could have m bigger than 2m. In that case, this thing here can be positive or negative depending on the value of x. So as I integrate in x, I can hit some places where this is actually negative or 0. Right? In that case, the logarithm will develop an imaginary part, right? I hit a branch cut in the logarithm, and I have to be careful, right? What I can do is use a well-known expression, right? That the log of minus a minus I epsilon, where a is positive, right, is given by the log of a minus I pi. Notice I'm only really interested in the imaginary part of this now. So that will simplify my life a lot, right? So let's use that. That means that in this second region here, let me get some space for me to write. Oops, what did I lose here? Oh, the, the, the A. Okay, let me move this over there, right? And I can write this logarithm here, right? Just have to call minus this part here A, right? This is, we'll call this minus A, and use that expression. That means that the imaginary part of this complicated log here will be just minus pi, as long as, and I use a half-side theta function to impose that, right? This is minus pi as long as this a is bigger than 0. So I just write a here, m squared x 1 minus x minus m squared. Right? So that imposes that I'm only considering, as I'm looking for the imaginary part of the log, the region where I can actually use this expression right here. Right? So I can plug that back into this integral as long as I'm looking only for the imaginary part of the loop. Right? Let me erase this one and try to get things from up there. Right? This means now, finally, that the imaginary part of this thing, right, is just, I get that minus up front, is just lambda square over 32 pi square, integral from 0 to 1 dx, right, of the theta function. That's all. Right? I don't have to integrate the log anymore because that's only important for the real part of this. Right? I still have to integrate the theta function. Right? That's many ways of doing that. Right? I won't do it. I won't do it here again. I can even do it in Mathematica. Mathematica deals well with heaviside functions. Right? This is just lambda square over 32 pi square, square root of 1 minus 4m little m square over big M square, theta of big M minus 2m, right? And this has all the nice properties you want, right? The fact that the theta after integration has become the very condition that phi can decay into twice the pi, right? Is 2 pi is already here explicitly, right? And now we can compare these to the what you would obtain for a decay, right? So suppose I go straight to this diagram and use the Feynman rules to calculate the decay of these green phi here into purple pi's, right? And mind the fact I eliminated already a pi square that was wrong here. I forgot to take into account this pi. So there was a lower power of pi in the denominator there. Right? So the Feynman rules for the decay are pretty simple. Right? These are all scalar states. There's nothing for the external lines. It's just really the Feynman rule for this. Right? And so the matrix element of phi going into 2 pi's, In this case, it's just lambda. Remember the Lagrangian, that was the coupling between them, right? Or I lambda. And that means that the decay rate of phi to 2 pi's, right? If we go back to those formulas from quantum field theory 1, right? We know that this has a factor of half here because the final particles are indistinguishable, right? And then it's just the usual formula for the phase space of 1 to 2 decay, right? So that's the 1 over 2 capital M integration of over d3p1 over 2 pi to the cube d3p2 over 2 pi to the cube 1 over 2e1 to e2. All these indexes 1 and 2 refer to these momenta and energy of the final particles here. Right? Then there's conservation of total momentum, delta 4 of p minus p1 minus p2. And of course, this matrix element square, which is just lambda square, right? And so we do the usual thing, right? There's 6 momenta integration here, but there's 4 Dirac deltas. That means we can solve most of these integrals and leave just 2 variables, which usually we choose the 2 angles, right? Write these in terms of the solid angle. Also going to the rest frame of the particle that is decaying, right? Where everything is easier. I'm not doing all these calculations again. We did it many times in quantum field theory 1, right? This is just lambda square over 4m, right? This is just the part that was already outside here. The integration over 4 of the 6 variables here will leave us with a d omega, which is the solid angle, over 16 pi square p1. Again, I don't care if I choose p1 and p2 because in the rest frame they are the same, since this particle and this particle have the same mass, right? The energies and momentum will be the same in that frame, right? So this is over capital M theta of m minus 2 little m. And this comes from, again, looking at where you have support for this Dirac delta in this case, right? You have to have conservation of momentum in order for the decay to happen, and that appears in that form here. Again, I can integrate all these things, go outside, right? All I have to do is really do the integration in the theta. Actually, in this case, it's just integration in angle, which nothing here depends on angle. This guy will actually become this square root, right? If you solve for this guy in that reference frame of the rest frame of phi, this becomes just lambda square over 32 pi square m. This guy, you can put a power of m inside him, and he becomes just 1 minus 4 m square over m, big M square, and this theta stays there, right? And now we can compare this, right, with this one. Let me see if I can find space. Yeah, you can see both on the screen, yes. So you see, I have the decay rate here and the imaginary part of the one-to-one scattering there, right? And the only difference between them, well, as long as I remove this spurious pi square here, should be pi, right? Because I have another factor of pi coming from here, right? I don't know what it is with pi squares and me today. But once I fix this, right? The only difference between the decay rate and the imaginary part of the one-to-one scattering is really this m right here. And we have seen the specialized form of the optical theorem to the one-to-one scattering, right? That the decay rate was just the mass times the imaginary part of this, which is exactly what I'm getting, right? So we can see that in this particular case, we are testing the optical theorem. And many times it can be easier to calculate the imaginary part of a loop like that, because all the complications in the integral are really on the real part, right? The renormalization, all of that, right? Then actually calculating the decay into many different states, right? So now, as a final subject for today, we want to finally go back to the unstable particles, right? So if you remember well, we have resummed the full propagator for scalar particles, and we have found that this full propagator can be expressed in this way, p squared minus m squared, in the renormalized theory, right? So this m can be anything depending on the renormalization conditions, right? But we also have this complicated function, big M square of p square, which is the sum of all 1pi contributions. Actually, in our convention, minus I m square is the sum of all the 1pi diagrams contributing to that, right? And then in order to define a physical mass, right, what we did was to say in the on shell, let's suppose we could do this in general in order to include also the MS bar schemes, but let's keep it simple and think of the on shell renormalization scheme. In that case, what we said is that this denominator calculated at the pole mass, right, at the pole, should be just m squared. That means this part here, this denominator has a pole where m is the physical mass, right? I'm defining the position at the pole at this number, right? And that means that this function calculated at that position should be 0, right? This is the on-shell renormalization scheme we used so far, right? But now we know, right, that this sum of 1pi functions develops an imaginary part, right, once this particle can decay, right? If this is an unstable particle, that means that there's regions of p squared, right, where this guy develops an imaginary part, right? And being unstable means that that is true in this region, right? Right here, you can already decay. Just think of the previous example, right? You had this particle which could decay because its mass is bigger than twice the mass of the pion, right? They say, let's call this phion and this pion, right? This guy could decay for p squared equal to big capital M squared if this condition was true, right? So in that case, imposing this condition would mean to impose this, right? That the real part of the 1pi sum. Be careful not to confuse capital M I'm using now for the capital M I used before. Now this means the sum of all the 1pi functions, right? So this condition would imply this, but also, and here is the problem, right? It would imply this, right? Remember that what we use these renormalization conditions to fix the counter terms, right? So this condition means that the counter term would conceal whatever contribution is coming from the 1pi, the loop part of the 1pi functions will be concealed by the counter terms, and then these would be 0, right? But now, if I do that, if I leave this imaginary part 0, I will break the optical theorem. I will violate unitarity, right? Another way of seeing that is, in order to make the imaginary part go away, I would have to give an imaginary part to the counter term to conceal the imaginary part for this 1pi function, right? But if I go back to the Lagrangian with a complex counter term, right? Just look at any of the Lagrangians we had and put a complex counter term. That will leave you with a non-Hermitian Lagrangian, right? Which again violates unitarity, right? So now we have to rethink our renormalization condition, right? Let's rewrite this guy in a different way. So let's expand this thing here to give us a little more space and actually write the real part of this. Here, I need even more space. And the imaginary part of this 1pi function. Now what I want to do, right, is to use a different condition for the pole mass, right? We call this the pole mass or the on-shell renormalization scheme, right? Now we use a different one, which people call the real pole mass, which is defined by this condition now. So I'm only including the real part of the 1pi sum in my renormalization condition, which imposes the usual condition, but only for the real part of the function. I'm leaving the imaginary part free to be whatever I get from the calculation, right? Now, if I take this, so this is called the real pole mass or the Breit-Wigner mass, and we'll see pretty soon why Breit-Wigner, right? So just think of what happens if I put this propagator, this full propagator now, inside some cross-section in the S channel. So I'm thinking that I just take this diagram, right, and plug it. Let me get a small thing like that, right? And I'm plugging this here. So I have some scattering. It goes through this propagator and then goes into whatever, right? So this guy is in the S channel. The cross section for this particular process, right, will be proportional to the modulus square of this propagator, right? It will show up somewhere inside, right? So this will behave like this propagator. Now I'm defining this as the mass, right? So I'll write it in this way, right? As long as I'm imposing the renormalization conditions, this goes away, and I'm looking near that pole, right? I'm looking in the S channel near p square equal m square. Just to be clear, p is the momentum going on here, right? But I'm still left with the imaginary part. So let me write it right here. I times the imaginary part of m square of s, right? So we know now that as I change, suppose I just take these two initial particles and change the energy, right? The center of mass energy, right? That means I'm changing S and looking at the output of this, right? At how the cross-section changes, right? Inclusively, let's say I integrate over all possibilities in the end, right? That means, oh, I forgot the square here. So that means these will be distributed in S as a distribution that we know, right? It's like peaked around m square, right? So this is big when S is close to m square, right? And it has some width, right? Of course, this width can be really wide or really narrow, and that depends a lot on this part, right? But let's suppose it is narrow, right? Let's first think of the case where the width is somewhat narrow, right? In that case, the whole contribution will come from this region where S is close to m squared. So I can make the approximation and replace here, I can replace the imaginary part of m squared of S by the imaginary part of m squared calculated at little m squared. Just because it falls down really quickly outside this region, right? So in that case, this is really the Breit-Wigner, right? As long as I make the following identification, right? Which is also inspired by the particular case of the optical theorem, right? Which is saying that m squared, the imaginary part of this guy close to the pole, right, is just the mass times the width, right? This minus is because this guy is really minus we have a minus here because I define the 1pi as minus m is minus the sum of 1pi contributions, right? I define it in this way. This is the sum of 1pi. So this minus here went there, and now we have to compensate for it. So in that case, this cross section can be written in this way. Let me just rewrite it. This is I over S minus m squared plus I m the width, right? In here I'm talking about the total width, right? Because again the one-to-one scattering is just related to the total width. And if I take these calculate this modulus square, this is just, right, S minus m square plus m square with square, right, which is the Breit-Wigner distribution, right? Not normalized to 1, because in this case there's overall strength of the interaction, right? So but the shape is like a Breit-Wigner probability density, right? So keep in mind that this is only good, right, in this approximation where this is narrow. Otherwise, I cannot make this substitution here, and I really would have to know the shape of this function, right, the imaginary part of this function. So keep in mind that we are assuming that m times this width is small compared to m squared here, right? Which means that the width is small compared to mass, right? Which is when you have a good shaped Breit-Wigner distribution, right? Now, and also keep in mind, this is very, this is equivalent, just to call your attention to it, right? If we go back, let me find the optical theorem for one particles here. So if I take this expression here, and copy it where we need it, notice that this approximation right here, this identification here, is the same as taking this equation. Let me delete the intermediate steps, right? This is the same as taking this guy, right? IM is equal to minus I, the 1pi contributions, plus whatever is not 1pi. So you have a lot of different things here. You have those diagrams with many bubbles, right? You have the full propagator, the free propagator. You have a lot of things here, right? This identification is the same as putting minus m squared in here, right? M is equal to minus m squared, which is disregarding all the 1pi contributions. So what I'm doing here, this approximation is equivalent of saying this guy is minus m squared of m squared, right? So there's two approximations. One is only calculating this guy close to where the momenta is substituted by the little mass square, but I'm also disregarding the known 1pi diagrams here, right? This is not very intuitive, but that's what having a narrow approximation amounts to, right? So then this becomes just, there's a minus here, as I have said before, right? This becomes just that this guy is minus 1 over m times the imaginary part of the 1pi sum calculated at this point, right? So this is equivalent to the approximation we're making there. So that's how these unstable particles behave. We can even take a more extreme case, right? Now suppose really that these the limit where these m squared times the width is really going to 0 now. I'm really narrow in width. In that case, we can exchange this distribution by the Dirac delta, right? With some normalization, so you just have to integrate these and get the normalization of here, but you will find out that this is it, right? Times the Dirac of S minus m squared. This is known as the narrow width approximation, and it is a very very useful approximation. Of course, exchanging distributions by just the Dirac delta is always useful operationally, but also a very good approximation for many particles, right? Because there's a lot of particles that really are produced, live long enough, and remember, low width means long lifetime, right? So that they always go on shell long before decaying, right? So particles that have a good narrow width approximation allow us to factor production from decay, right? Let me copy this diagram just to make that clear, right? What happens is that essentially for particles that satisfy these, you're imposing on-shell intermediate state, right? So diagrams like this, say a diagram, something happens, this guy is produced, and then it decays, right? Usually you would have to calculate the whole thing with a virtual propagator here, but for particles where this is a good approximation, essentially you have to calculate this part, which is the cross-section for producing that particle, times the decay of that particle, because it's always essentially on shell, right, before it decays. And you can do this, just the multiplication of these two probabilities, because there's no interference between what happens in the production part with what happens into the decay part, right? They are really narrow, and basically nothing happens when this propagator is even a little off shell, right? No contribution comes from the off shellness of this particle, right? The opposite limit of that, suppose we want to look at the opposite limit, right? Everything we did from this point down is not valid, right? Now, I really have to take into consideration this propagator, where both the real part and the imaginary part of this have important contributions away from the pole position, right? It matters, the shape of these distributions matter, because the actual distribution you see in the S channel, for instance, will be some wide resonance showing up. And at that point, it's understandable that this condition for defining the physical mass is not good, because it's even ambiguous from the experimental point of view to define what is the physical mass of this thing, right? Because if you look at the decay that comes from this position, right, you will reconstruct a particle that has some mass, right? You just have to look at all the decay products and sum the total energy there and total momentum, and then use the relativistic dispersion relation to get a mass. But if you do for a decay that happened here, right, this is another event, right? This is like a histogram for your experiment. You get a different mass. So it's not even clear which one you should call the physical mass. And the reason is that particles that decay with large widths, right, and have a huge deviation from a narrow bright width, it's not even clear that we should call these guys particles, right? Because they are never really on shell, right? They are just decay, they're just intermediate channels from these initial particles to these final particles, but they are never really going on shell. And also, as the width increases, the lifetime decreases. So at some point, these particles will never get to your detector either, right? So you'll never see these as particles, just as reconstructed objects, right? Virtual propagators, right? Virtual particles in the combination of momenta and energy for the particles that actually get to your detector. So you see, when the width starts to get really big, these are not even particles anymore. So it's understandable that the on-shell renormalization scheme gets really ambiguous, right? Really, because these guys are really ill-defined as particles, right? So, and there's a continuous behavior from the really narrow particles, which are easy, to the really wide ones, which are also easy. You don't call them particles. In the middle, you have these gray area states, which you could treat as particles in some approximation, but it's really just an approximation, right? That's the important conceptual thing to understand from this discussion, which is really particles are really only these states which have a very good narrow width approximation, even if they are unstable. Of course, if they are stable, this is the best approximation ever, right? They never decay, the width is really zero, and this is perfect, right? So this is, I think this is the message for the day, right? Thank you, and see you on the next one.